Okay, welcome to part 2 of our notes on electric circuits. Today we're going to parallel circuits. And what they mean for the home. So when we look at parallel circuits, the key to remember with a parallel circuit, and you've seen this word and we've talked a little bit about it because it is up on the word wall. Parallel circuits are circuits where there's more than one path for the current to flow through. So that means there are multiple branches for the current. So there are some things to keep in mind when we talk about this, and always keep in mind two things. Number one, things to always remember when we look at circuits is that we always say this, and energy must be conserved. We've talked about that before. That's the law of conservation of energy. And number two, matter must be conserved, and that's the law of conservation of matter. So we can't make energy out of nothing, and we can't destroy energy, and we can't make matter out of nothing, and we can't destroy matter. So what does this have to do with parallel circuits? Well, let's say we've got a simple pair of D-cell batteries. We'll say we have two of them. So we have 3 volts total. Two 1.5 volt D-cell batteries. And coming out of those we'll have a wire. And that wire is going to have 2 branches that it can go through. And it's going to go through if I said 2 I meant 3. 3 branches. We'll do 3 bulbs. 2, 3 light bulbs. So we're going to have 3 light bulbs for this to go through. And we'll say each light bulb has a resistance of 3 ohms. We'll do them all the same to start. So 3 ohms, 3 ohms, 3 ohms. Okay. So as we saw in the lab, when we measure the voltage from one side of the bulb to the other side, if we hook our voltage probe up to this, and we connect one side and the other side to each side of the voltage probe, what we're going to find is that voltage is going to be the same as if we connected directly to the battery, and we would get 3 volts. And we saw that in the lab. No matter where we put these probes, we could leave it at this end, or we could move them so that they are further down in between here and here at the green points, or we could do them here and here at the 2 purple points. It doesn't matter where we put it. No matter where we go, the voltage across each of the branches is the same. And that goes back into that conservation of energy thing. That path around the circuit, we have to have the same amount of energy in has to equal the same amount of energy down. So we're really looking at 3 paths here. Each path has to conserve energy. And so no matter how many ways you go around, what we end up seeing is that voltage has to be the same. So if the voltage is the same, then we can start to look at we can talk about how current's moving. So one of the other things we saw is if we measure the current going through this circuit, and what we would find for this current is we would have, through each one of these bulbs, we'd have 1 amp going through. If the resistance is 3 and the voltage is 3, then 1 amp is going to move through each one of the bulbs. And what we also saw was that the current coming out of the battery was all of those currents added up. So it means we have 3 amps coming out. And that is the first of what are called Kirchhoff's laws. And the first one is current. The current law is that all of the current into a point must equal current out of that point. So when we have these 3 branches, what we end up seeing is currents going through each one of them. And if I was to measure the current here in between the purple and the green branch, what we'd find is here it's 2 amps. And then this last one, it's 1 amp. So coming into the green point, we have 1 amp, we have 2 amps going in and 2 amps coming out. Going into the purple point at the top here, we have 3 amps going in and 3 amps coming out. So again, as we move around the circuit, that energy is conserved, or excuse me, that current is conserved, and that again goes back to matter. You can't destroy these electrons, and so it has to be conserved as we go around the circuit. So if we're talking about voltage, like we said, the voltage was across the same, and that goes with energy. Let me go back. So we're looking at how we go around. No matter which way I go around, I'm going to have the same energy up. That's at 3 voltage up. I have to lose that energy no matter which path I take. If I send an electron around through the purple branch, it needs to lose 3 volts. If I send it through the green branch, it needs to lose 3 volts. And if I send it through the red branch, it needs to still lose 3 volts. So again, we're looking at energy being conserved as well. So no matter what, the energy has to be conserved. So how does that apply to short circuits? Why are short circuits so bad? So again, a short circuit is when we have a path with little to no resistance. So let's say we have a 1.5 volt D cell and it's connected to a 1 ohm resistor. Well, if that's the situation, voltage is current times resistance. So the current through that 1 ohm resistor is the voltage divided by the resistance. So current is 1.5 divided by 1, which is 1.5 amps. Which is fine, 1.5 amps. Nothing too crazy, normal. If we create a short across that, still have the same resistor, but we add another path where there's no resistor. The wire still has some resistance, and it's going to be really small, about 1/1000th of an ohm. So the voltage across that is still 1.5 volts. But now the resistance is 0.001 ohms. So do the math. What's the current going to be? 1.5 divided by 0.001 is going to give you about 1,500 amps. And that's a lot. If the battery could put out that many amps, over 1,000 amps, the wire would pretty much melt right away. But batteries can't react that fast and they can't keep up, so they don't melt right away, but they do get hot and it does drain the battery. And the battery gets hot too, and we've seen that in experiments and stuff in the lab. So the last thing I want to talk about is the resistance here. So one of the things we see with resistance in parallel circuits is something really important. So let's do this. Put a star there, very important. So more paths lead to more traffic. Think of it this way. If I have one road to get from a house or a neighborhood to downtown, that's a really bad drawing of that building. If I only have one road to get through, then every car has to take that path. So, but as I add more roads around the city, I can get more cars to downtown. More cars can travel if we have more roads, and circuits are the same thing. So more paths, more branches lead to less resistance. That is, I can get more electricity to flow through the current through the circuit if I have more resistance. So, what we end up with is this. The resistance of the circuit is the inverses added together. So the inverse of the resistance is all the inverses added together until we get to them all. And again, it goes back to more paths mean less resistance. So before, as we added resistors, it was harder for the current to go through. Now as we add resistors, it becomes easier for the current to go through. So let's practice with that. Before, if we added three 3-ohm resistors together in series, it would be 3 plus 3 ohms plus 3 ohms, and we'd get 9 ohms of resistance. But now if we add them together in parallel, it's 1/3 plus 1/3 plus 1/3, which equals 3/3, which is 1 ohm of resistance. So the exact same resistors arranged differently give us a much smaller resistance, which means more current, which could mean too much current, but not necessarily. Alright, so we're going to work with the math a lot more in class, but consider this equation something really important that you need to remember. The same level as the series circuits and the same level as the voltage, but we'll practice more in class. Alright, I guess I'll see you tomorrow in class. With your notes, have a wonderful night.